Hello. The purpose of this lecture is to give an overview of the basic concepts and terminology related to partial differential equations, or PDEs for short. And on a very general level, PDEs are differential equations where the unknown function depends on several variables and the equation itself involves partial derivatives with respect to more than one of these variables. And here on this slide, we have three different examples of typical PDEs. And if we look at, for example, the first line, here the unknown function f depends on two variables, x and y, and the equation itself involves the second order partial derivatives with respect to both of these variables. And the most typical variables encountered in the PDEs that model real-world phenomena include the spatial variables x and possibly y and or theta, depending on whether we're considering one-dimensional or multi-dimensional situation. And also the variable t, denoting time, is a very common variable to include in such models as well. But it should also be noted that other variables are possible as well. On this course, we are mostly interested in PDEs that do include time t as a variable, and these PDEs are called dynamic. And such PDEs can be used to describe several real-world behaviors evolving over time, such as vibrations and waves, flows of liquids, electromagnetic fields and radiation, and diffusion of heat and materials. And of course, also PDEs that do not include time are also very common in modeling, and they can be used to describe, for example, forces and stress in materials and mechanical structures. And of the two examples given here on the slide, the first one is static and the second one is dynamic, as it does include time t as a variable. On this course, we also concentrate our attention mainly to linear PDEs, where the terms do not include products or powers of the unknown function or any of its derivatives. And this is a strict subclass of partial differential equations because most PDEs are, on the contrary, nonlinear ones. For example, of the two equations on this slide, the second one is nonlinear due to the first term on its right-hand side, which includes a product between the unknown function f and its derivative. On the other hand, the first equation is linear, since linear equations are allowed to contain products of the unknown function and its derivatives with some known coefficient functions like a and b here. And from the modeling point of view, linear PDEs are still an important class, because many natural processes are linear, or at least linear with sufficient accuracy. And in addition, also many nonlinear behaviors can be approximated under suitable assumptions with linear PDEs. As PDEs are complicated objects, the questions of the existence, uniqueness, and general properties of their solutions are very interesting, and they can be mathematically very challenging to answer. And in these regards, linear PDEs are much simpler than nonlinear ones, but even in the linear case, there are many interesting open problems. On the nonlinear side, there are many PDEs that are known to be very challenging from the solvability point of view, and there are also many equations whose solvability is under very active study in the literature. The prime example of such equations are the Navier-Stokes equations that describe the flow of viscous fluids and are used in particular in the modeling of the climate and the weather, among various other things. And as these questions are very challenging, we do not consider them in detail on this course. But of the general properties, it should be pointed out that in order for the PDE to make sense as an equation, the partial derivatives that appear in the equation should make sense in a suitable way. And there are many different ways that this, in a suitable sense, can be defined, but usually this implies certain continuity or differentiability properties for the solution that we are looking for. And we can now move on to the basic concept and terminology of PDEs. First, we have the order of the PDE, which simply means the order of the highest partial derivative appearing in the equation. So in the equations written down here, the first equation is of order 2. The second one is also of order 2 because of the first term on the right hand side. And the third one is of order 3 because of the last term on the right hand side. If the PDE involves spatial variables such as x, y, and zeta, then the spatial domain of the equation means the range of these coordinates for which we want to find a solution. And the domain itself is usually denoted very clearly when the equation itself is presented. For the first equation on this slide, the domain of the equation would be the unit square ranging from 0 to 1 in both of the coordinates x and y. And on the other hand, if we want to model the heat distribution in a room with dimensions L, D, and H, then the domain would be the three-dimensional region determined by the lengths of the sides of the room. For PDEs with the time variable t, we usually consider the equation starting from some fixed initial time t0. And to get a unique solution, we pose an additional condition that the solution is some known function at this first time instant. And this is called the initial condition of the PDE. And for example, when considering the evolution of the temperature of the air in a room, the initial condition states that the temperature profile is given by some known function g at the first time instant of the equation. Similarly, solving PDEs that include spatial variables requires knowledge of the behavior of the solution on the boundaries of the spatial domain. And the most common types of boundary conditions are the Dirichlet and the Neumann boundary conditions. The Dirichlet boundary conditions pose conditions directly on the values of the unknown function on the boundaries of the domain. And for example, these values can be given by some known functions as shown here on the slide. In a very typical situation, the solution may be required to be 0 or some other constant value on all of the boundary. And on the other hand, Neumann boundary conditions instead require that the normal derivative of the solution should have specific values on the boundary. And one typical situation is where the normal derivative is required to be 0 on a part of the boundary, because this physically describes the situation where, for example, heat or material does not flow through this part of the boundary. And finally, it should be also noted that the initial condition we considered on the previous slide is also in a sense a boundary condition on the time variable t, but it is given a specific special name due to the interpretation of this variable. One important thing to note is that in order for the solution to be well defined, it's essential that the conditions we pose are compatible in the sense that the initial condition also satisfies the boundary conditions. The general theory of PDEs also makes it possible to consider solutions for which this is not true, especially using weaker definitions of the solution, but such techniques are not considered on this course. Outside the simplest cases, it is impossible to find an explicit expression for the solution of the PDE. And because of this, approximating the solutions numerically for the purposes of illustration and study are important in the study of PDEs. And there are several different approximation methods, but the main simple ones are the finite difference method and the finite element method. In the finite difference method, the domain of the PDE is divided into small rectangles or cubes, and the solution of the equation is approximated at the corner points of these rectangles. And one of the advantages of this method is that it's very simple to implement in the case where the domain is rectangular. The finite element method is a more advanced numerical approximation where the domain is divided into a grid of triangles or higher dimensional simplexes, and the solution of the PDE is approximated using a certain set of hat functions or basis functions associated to this grid. This method is more challenging to implement, but there are also a number of complete programs and codes that can be used in the approximation, and the method works very well for more general spatial domains. MATLAB has two main functions for numerical approximation of solutions of PDEs. In the simple case where the PDE only includes two variables, it's possible to use the built-in function PDE-PE. In addition, the PDE toolbox can be used to consider PDEs that have either 2 or 3 spatial variables and possibly the time t. And on this course we'll use the function PDE-PE to illustrate the solutions of the hidden wave equations that we'll consider in detail in the later sections.